All right, so my name is Xun Gong. I'm a faculty member in the EC department, and my lab is called Antenna, RF, and the Microwave Integrated System Lab, Army Lab, and the link is shown below. So a little bit of my background. So I joined the UCF in 2005 as an assistant professor, and I was promoted to full professor in 2017. And also, my lab is called Army Lab. It's located in HEC, and also a small part of my lab is in one of the lab in Engineering 1. So in our lab, we have a lot of equipment which are used for high frequency components characterization. So we have high-end equipment such as network analyzers, working up to 170 gigahertz, and also we do microfabrication of particularly those high frequency millimeter wave components and antenna in clean room. And as for teaching, I'm the technical area chair for electromagnetics within the EC department, and most of the courses I have taught are in the electromagnetics area, covering from undergraduate to graduate levels. And I have been mainly my technical society in the IEEE is microwave theory and techniques, and the other one is antennas and propagation. And I have taken many roles in the society. So certainly I'm not going to read through the entire, all the bullets, which will be posted online for you to read. And primarily I'm going to talk about several recent research directions my group has been pursuing. One is the filter antenna integration. So we aim to integrate the RF front-end system together with multiple functions within a small form factor. And we use it to create novel devices, even including wireless passive sensing using this particular technique. And also I'm going to talk about the multi-band antenna arrays with wide bandwidth and polarization agility. And also I will talk about the electrically steerable parasitic array radiators. And these are in the category of, for the high performance and multifunctional antenna arrays, which can support the multiple operation goals. And also last, I will talk about the beam scanning reflector arrays, and what are the research associated with that. And many of those researches have been integrated into my teaching, such as, the 3 courses I have listed here. So first thing I'm going to talk about is the filter antenna integration. So it has been supported by a couple of projects based on different missions, using what kind of thing we're going to do that. So for example, one of the application we do is that for this particular graph, we can see that we can integrate those antennas vertically with those high performance filters. And more importantly is that we are one of the first groups to figure out how do you integrate them in a seamless fashion, which means that in the past people designed them separately and then they integrate them together. Not integrate, they connect them together. But we are one of the first groups to figure out that how can you actually design the entire thing as one device and achieve the highest performance. And this is one of the highlights we recently achieved. And so basically, the goal is that we want to embed the filtering functions inside of the antenna array so that you can reject the interference much better compared with the one without. And also we can significantly reduce the loss compared with the traditional approach that you design the filter and antenna separately, then you put them together. And usually it's a much more compact in the form factor. But also we could utilize this concept, the design concept, to develop high temperature sensors for example, combustion turbine applications. So this is a wireless passive sensor, which contains one antenna and also a sensor, which is a resonator in this case. But we have a way to design the 2 functions within one device and make it relatively compact and high performance. And also we could use this similar concept to develop the sensor for the biosignal sensing. So for example, this one is that a collaboration between me and one of my colleagues to develop the wireless passive sensing of the temperature for patients. So we could integrate this antenna with a very tiny MEMS sensor so that we can actually place the sensor on human skin and we can sense the temperature variation without intrusion. So which means that the information will be taken basically through wirelessly. And so this is one of the the research work I have done, and I think that this particular technique can be implemented to, for example, 5G systems or 6G systems. And for example, I recently read that for 5G system, actually the power consumption is a big deal. So we actually using our technique might be able to significantly cut down the power consumption, and also in the sensor area as well. The next thing I'm going to talk about is a reconfigurable antenna. Right now, this one has been mainly supported by Ph.D. projects, which they would like to see that you have a one antenna aperture, but it supports multiple operations, so that you don't need multiple bulky antennas anymore. You only need one aperture, then you can use it for different applications, radar and communications. So this is the product hardware we developed so that we are able to support multiple frequency bands. For example, here, this particular aperture can support S-band 224 gigahertz and the C-band within the same aperture with some reconfigurable devices embedded inside. Secondly, is that we had some innovations to adopt the fractal shapes in order for us to have a very wide bandwidth. And certainly it supports multifunctional design, and it's modular design so that we can extend it to a larger array without any redesign. So this, I believe that it could be applied to many civil applications or military applications, using this kind of a multifunctional antenna aperture. And the last but not the least is that we had some approaches, talking about how we actually created the low-cost beam-steerable array. So one approach is that we use a so-called reflector array approach. So you can see that we have a flat aperture which you can, reflect the beam from the whole antenna. However, we are able to make it a beam-steerable using the tunable devices embedded within the antenna aperture. So this is one approach we did. The other approach is that we're using an S-bar approach so that we can put the small tunable devices. Actually, we use their tuning elements, but also we actually utilize the parasitic coupling between the antenna elements to achieve the beam steering, which actually can significantly reduce the number of the phase shifter, which is quite expensive and lossy. So we believe that this can be used for many different applications, such as again 5G, 6G application, and also in many other coming for example sensing network, those kind of applications, due to the low cost and certainly affordability and the relatively easy design approach. So the opportunities, I think that I have been working with many colleagues in and out of my department. So for example, I work with Professor Murat and Azadeh, working on the, for example, we recently got a project on NSF, is a software-defined radio at the millimeter wave frequency using beam-steerable reflector arrays. And I also work with Professor Kenle Chen on carrier aggregation at the millimeter wave frequency. And I work with, also with Marty on the novel transceiver architecture at the millimeter wave frequencies using filter antenna integration. Working with Professor Reza Abdulban on this on the sensor design. And regarding the sensor, also recently we had a small SBIR project from working with professors in mechanical engineering department, Karim and CSAT. And I think that in general the technique we have, the RF frequency multifunctional antenna array and passive components, I think that it has a lot of opportunities to work with people who are working in the circuits area, the communications area, sensing area, and for example, health monitoring on the structures, for example, or actually structure monitoring, for example, this is something I might be able to work with a mechanical engineer or civil engineer, and just to name a few. And I think that's pretty much my presentation. Am I on time? I think I'm pretty much on time, right?
Yes, you are good.
Okay, and this just shows some, a list of my sponsors for the previous project. All right, so that's all my presentation, and I will be happy to take questions.